Assalamu alaikum. My name is Omar Tahboub. I will probably be your mentor today to introduce you to the world of blockchain. It's a really interesting topic. Everyone is talking about it in the market and the IT scene and cybersecurity in general, because it does not only include database uh, the concepts. It includes a really big chunk of cybersecurity. First and foremost, we need to understand that blockchain is not a traditional database. Um, it cannot be queried nor modified, and designation of this cutting-edge technology offers high security in a manner that it's computationally infeasible to break. We'll get to that in a second, by the way. Moreover, it somewhat serves the concept of the CIA. For those who don't know, CIA stands for, it's not the American Central Intelligence, by the way. It stands for confidentiality, integrity, and availability. These are the three assets of information in cybersecurity. We will also show a procedural demo of the blockchain later on today. But for now, let's hop on to the presentation. Well, hello again. So let's start with our presentation. Why do we need blockchains? Blockchains are a collection of records. They are linked with each other, just like every other database. That's the common part. But also, these 2 points, as we said, they are shared by all databases. The next two, these are the new fashion here. The data is strongly encrypted and it cannot be altered or modified. It's resistant to modification or alteration, and it's protected using complex encryption algorithms. We'll get to that in a second. The difference between traditional databases and blockchains. These are the key differences between the two models. Um, let's start by talking about the data. The data in the database is mutable, where we can say that it's editable, it can be modified, it can be altered. While on blockchain, it's immutable. It's created once and never change again. In database, the data relies on a centralized security measures. How do we understand that? Let's imagine this scenario. We want to transfer an amount of money to a friend through a bank service. It needs to be viewed by the bank authority to either approve or disapprove the transfer. While in blockchain, we don't need that. The main feature in blockchain that it's decentralized. It uses cryptographic techniques, consensus, and decentralization. Databases also provides private and managed by a central authority like a banking transaction, as we mentioned before. Blockchains, as we said, it's public and transparent, and it's actually viewed by a network of nodes that can actually approve or disapprove. It plays the role of the bank or the centralized party uh, that decides whether to approve or disapprove the transaction. Database, it's a real-time high-performance application, while blockchain, it's a secure, transparent application. It's like cryptocurrencies, like contracts, like records, healthcare, maybe voting systems. All voting systems, by the way, are encrypted by, let's say 90% of them, they are encrypted by blockchain. So we can deduce that the main trend of the blockchain is high security. The idea of key distribution offers a sophisticated layer of security. Public keys are shared to a network of nodes, but only the sender and the receiver are the permitted nodes to decrypt a digital signature that is included in the message. It strengthens accountability and non-repudiation when performing related forensics on the data transfer operation. We'll get to every detail of that in a second. Bitcoin, it's not the only one, but it's the first application of blockchain. It's the most famous one. Whenever you hear the word Bitcoin, the always linked phrase to it is blockchain, because actually Bitcoin relies hugely on blockchain because it's encrypted using a peer-to-peer technology, and that's the main core of blockchain. Let's go here. Okay. Blockchain follows an open ledger concept. What does that mean? Every transaction is scanned by all nodes in the network. So an open ledger means that the records they are accessible to everyone in the network, and this ensures transparency and accountability. And it also helps in the forensics later on when anything related to the data is wanted to be, let's say, uh, uh, tested, for example, or we want to check something. A public key is broadcasted to the nodes in a network, and a private key is only acquired by the user and the sender. That's what the concept of an open ledger mean. Let's go to hashing. Hashing it is the backbone of the encryption process. It is a regular hash function. It basically generates a fingerprint from a plain text. And that fingerprint, for example, the word hi, it can have only a unique hash value. Um, Additionally, it records the hash value for the current block and the previous block in the blockchain. Um, just to make things simple for you, the blockchain is actually a collection of blocks, just to be simple. Um, so we either add a block or remove a block. So two hashes must match in terms of the current block and the previous one. They must match in a manner that uh, we either approve or disapprove a transaction. Hashing is used on blockchain to apply confusion to any possible intrusion. It basically converts string to hash value, and any change in the string results in changing the whole hash string. We'll show a demo on that actually to show you how it actually it's a unique length of the string, but it changes just if we change one character or one bit. Each block in the blockchain has a hash of its own value and the hash of the previous block. We can deduce that the alterations are vulnerable to detection. Transactions are verified and trustworthy without needing a central authority. These are the most famous hashing algorithm used by various cryptocurrencies, but the most famous one is SHA and ETHASH. SHA has many versions, but the newest version and the most, let's say, powerful one is SHA 256. Litecoin and Dogecoin use script, and Ethereum use Ethash, as we said. Mining. It's actually the most interesting part in the blockchain technology, in my opinion. Uh, Indeed, it is what made the blockchain stand out between other technologies. It is a process where a transaction is monitored by the miner nodes, and decision is made in either to approve or disapprove the transaction. Miners does not necessarily need to be people. It can also be other parties or other entities like a mining pool or mining farm. By the way, this concept in some countries is not permitted. It's considered maybe playing with the currency rates and uh, just making changes that are not permitted by the country guidelines. That sketch actually it shows how the miners work in the blockchain network. So we have let's sketch it actually. We have a node A and node B. A is sending $10, for example, to B. It's hashed Okay, it's hashed and it's sent to B. Sorry for the great handwriting. We have other nodes in the network. C can have D or E. Um, either for approving or disapproving the transaction, it needs to solve a mathematical equation, a complex one. That's the function of the miner. It needs to solve the mathematical function that gets the hash value. So if it happens to match the hash value that is sent to D, then the transaction is approved. Otherwise, it's not approved. So let's visualize together how a blockchain system works. First, we have to start by showing how the hash value works. So let's type a random word. Hello. So that's the hash value for it. If we type another string of another length, it will also generate a hash value of the same length. Even if we had multiple words in a sentence, it's going to generate the hash value with the same length, and that's where the strength of the hash value um, is present. So here we're having a single block of blockchain. We have a new field here that is the nonce, and we have the data that we have previously entered in the hash section. The interesting part here is that the nonce can be changed, but once we change it, once we change it, we need to mine a new hash value. It's actually not a new hash value, but it generates the same old hash value, but it needs to mine another mathematical equation to generate that hash value. It's a really complex problem here. So let's, for example, type 45. It gives 00F. See, it gives the same old nonce and the same hash value. Let's move to the blockchain. We have the blockchain in here, which is actually a collection of the previous block that we have discussed. We can see here that it contains the hash value of the current block and the hash value of the previous block, and they are if this one and this one are not matched, then the whole thing breaks, and that's where the disapproval happens. So let's, for example, you are probably wondering what's the mine button here. So here, let's imagine the nonce that is a serial number of the blocks. So if we change it here, the whole hash is different, and when it's different, it's gonna affect the other blocks, which are gonna change every other block, and the blockchain is gonna be broken. So when we press mine, it finds a suitable mathematical equation that finds the correct hash that should be transferred to other blocks. Here in the distributed blockchain, it's very similar to the previous model shown. But here we can say there's a connection between blocks. Um, Here we have the same functionality. If we change the hash for if we change the nonce for one, it's gonna break the hash and the previous hash, which will affect the other blocks. But there's an interesting part here. These blockchains in the peers, they are identical. But for example, if we entered some random data here, hello, and we mine it, it looks fixed here, no? But if we checked the other peers, they are let's say a carbon copy of the previous peer, we can see that the hashes are different. So that's the place that we spot that there is an error in the system, and we report that the transaction must not be approved. That's a practical example on the blockchain. That's a money transfer example. So here we can say that Darcy is transferring $25 to Bingley, and that's an ons. If we change it here, we can do the same stuff that we did in the previous examples. It's going to take a while. And for the peers, let's try to change the numbers here. The hashes will be different as in distributed. Here we must mine it again, and here as well, and here. But we can see that the hashes are different. The first four numbers after first four characters after zeros are 5B53, and here is C529. Um, and that's where the error happens, and we also report the disapproval of the transaction. But there is an interesting part. There is no like a balance for every person. And nonce here is a person, and the other nonce is another person, and it just shows that there is a transfer from person A to person B, but we don't know the balance for each person, so we don't know if actually the transaction is valid or not. We're going to see that in the next example. Here we have added another field in the Coinbase. It is the Coinbase. Okay, so here it tells that Anders have $100, so that's the credential for Anders. So when he transfers all that money, we can deduce that it's still there's still some balance in his account. And that's another way of validating any transfer in a blockchain manner. I think that's all we have for today. Thank you for watching, and goodbye.